Draw the shear and moment diagrams for the beam. To begin, let's convert our distributed loads into point loads. So we're going to have on the left hand side 1800 pounds. The right hand side will be half times 600 times 12. Comes up to be 3600 pounds. And then we have a ruler at A and a pin connection at B. Horizontal direction at B is going to be 0. And now to find our AY, we're going to have to take moment about the point B. We're going to have 3600 pounds and it's 8 feet away. Then we have clockwise AY, 12 feet away. And we have counterclockwise 1800 pounds, 14 feet away, all equals to 0. Solving for our AY, we get our solution as 4500 pounds. And then to find our solution for BY, we simply have to sum the forces in Y direction. So we're going to have negative 1800 and 3600 and positive 4500. Solving for this, we get our solution for BY as 900 pounds. Alright, now that we have that done, this time we're going to do things a little bit different. So instead of our regular looking for our equation or functions and then solving for the shear and the moment diagram, this time we're gonna draw the diagram and then look for the shear and moment functions as required. Alright, so to begin with our shear diagram, let's get the initial layer set up. So for our shear, we're gonna begin at 0, we know for sure, and then tell for the first 6 foot we're gonna go downwards and it's gonna be second order curve and it's gonna be concaving downwards. We don't know how far down it's gonna go. That we can find through our point load, which was 1800. So we know we're gonna go down negative 1800, and then our AY is gonna push us upwards. That's 4500. So 18 take away 45. We're gonna go up by 2700 points or pounds. From here, we're gonna go down 3600 pounds over 12 foot or feet. That will take us to negative 900. And again, our curve is going to be concaving. Well, in this case, it's going to be concaving upwards. And it's going to be second order curve. And from the negative 900, BY is going to push us up all the way to the 0 pound mark. And this confirms our diagram was correct. I can already see that I will need the functions of shear to find our intersect in order to determine the min or max of our moment, but we'll do that later. Okay, now for our moment, we're going to begin at 0 and then we have this area, negative area, and this curve was second order, so our curve for moment is going to be third order. We don't know exactly the end point where it ends. For that we'll need our function, but we don't know that it's going to go downwards just like the shear. And from there we're going to go up till this intersection at the shear, and this is going to be our maximum point for the moment curve, and it is going to be concaving downwards, but we don't know the maximum point here just yet. And then from there we have this negative area that's going to take us all the way to 0, concaving downwards. So what this tells us is we'll need our moment and both shear in order to solve this graph. So let's go back to our beam diagram, and in here we know that there's going to be two separate regions. We're going to name region 1 and region 2. Okay, so to begin with the region 1, our load equation is going to be rise over run. So we know that we're going to end at 600, beginning at 0, and for distance we're going to end at 6 feet and begin at 0 feet, and it's going to be our x. So this means we're going to be, our load equation is going to be negative 100x. Now for the shear, you just have to take the integral, so we're going to have negative 100 times x squared divided by 2 plus the constant. And to find the constant, we know we're going to begin at 0 for shear, and our x is going to be at 0 at that time, so our constant is 0. Therefore our shear equation is negative 50x squared. And now we're going to take another integral and convert our shear equation into our moment equation. We're going to have negative 50x cubed divided by 3 plus the constant, and our constant again is going to be 0 because moment is 0 and x is 0. So we're going to be left with negative 50x cubed divided by 3. Alright, now we can use our shear equation to find the intersect, but we can't really because that intersection is in region 2, but we can find out our moment for the minimum here. So it's going to be negative 50 times 6 cubed divided by 3. And this comes up to be negative 3600. So this point here is going to be negative 3600. And now to find our peak, first of all we need our load equation for region 2. So in this case we know it's going to be rise over run, so we end at 0 pounds, beginning at 600 pounds. Our ending distance is 18, beginning is 6 feet, times x plus the constant. Alright, so now that we have this equation here, we have to find our constant. To find our constant for the load equation, we know our load is going to be 0 when x is 18, and solving for this, we get our solution for C constant as 900 pounds. So we'll plug that into our load equation, and that's our solution. And this is 50, so this will be 50 here. Okay, and it'll be negative 50. Alright, so now we can take the integral of the load equation to find our shear equation. So we're going to have negative 50x squared divided by 2 plus 9x plus the constant. And to find our constant, we know our shear is going to be negative 900 when as x is 18. We can take any point, but I just took this because it was one of the easiest, times 900 times 18 plus constant. Our solution for constant is 9000. Okay, now we can take another integral for find our moment function. So it's going to be negative 50x cubed divided by 3 plus 900x squared divided by 2 plus 9000x plus the constant. To find our constant, again, we know that our moment is going to be 0 when x is 18. So we can have 18 cubed divided by 3 plus 900 times 18 squared divided by 2 plus 9000 times 18 plus the constant. Solving for c, our constant, we get a solution as 259,200. Alright, rewriting the moment equation. Now before we proceed, I want to confirm that our values are correct. We will begin with our shear. So for shear, we're going to say, let's see what the value for shear comes up when x is 6. So we're going to have negative 50 times 6 squared divided by 2 plus 900 times 6 plus 9000. Solving for our shear equation, there seems to be an error because we're getting a really big number, which is 13,500, when in reality we should have just 2,700 positive as our solution. So let's go back and let's try to see what we did wrong. So let's go back to our, first of all, our load equation. And in here we know that we're going to have our solution as negative 600 divided by 12, and dividing that by, we get our solution as 50, negative 50. And I think we have found the problem. This negative 50, and then there is another negative from the load being in the negative direction. This would have been a positive here. If this is positive, this means that our solution for C is going to be negative 900. This means our solution is for load equation was going to be positive 50x take away 900x. And now our shear equation is going to be different as well, because now we have positive 50x squared divided by 2 take away negative 900x plus the constant. And to find our constant, we know that we have 50 times 18 squared divided by 2, and then we have negative 900 times 18, which comes up to be negative 8100, and then we add negative 1800 on both sides, so we're going to have 7200 as our solution for the constant. Now going to our moment, we're gonna have positive 50 x cubed divided by 6, negative 900 x squared divided by 2, and then positive 7200 times x plus the constant. Now to solve for our constant, we get the value for constant as negative 32,400. Now let's verify if our equation is correct this time. So for shear at 6, you're going to have 50 times 6 squared divided by 2, take away 900 times 6 plus 7200, and solving for the shear we get our solution as 2700, so that's correct. And now let's verify our other equation. We know our moment is going to be negative 3600 at 6, so let's see if that is correct. So we're going to have positive 50 times 6 cubed divided by 6, take away 900 times 6 squared divided by 2 plus 7200 times 6, take away 32,400. Solving this, we get our solution as negative 38,600, so that's correct. Alright, so now that we have our equation set, let's find out where the intersection occurs for the region 2. So we're going to have shear as equals to 0, positive 50 x squared divided by 2, negative 900x plus 7200. Solving for x, we get our solution as positive 12. So that means this intersection is at 12 feet. And now we can plug the value of 12 into our moment equation to find our max value for the moment. So that's going to be 50 times 12 cubed divided by 6, take away 900 times 12 square divided by 2 plus 7200 times 12 plus or negative 32,400, which is our constant. Solving for the moment, we get our solution as positive 3600. So this means our max point for moment is 3600, and then we come down to 0. And with that, we have solved our